let's start. Yesterday, we are discussing the subspaces. And also we discussed that some set of vectors, will that be subspace of, in general, let's say the R3 or not. The example 6, so there is a set of vectors, a family of vectors, and they form a subspace in R3. Okay. So in other words, we can say that this set of vectors, generates the subspace. Okay. I mean, so this is the whole subspace, but okay. So I talk just little later about the generation of a subspace. Okay, in the example 7, this set of vectors is not a subspace, and 8 it's also not a subspace. In 9, this is a subspace. And what we see that here, when we recapitulated here, in this case, the example 1, this example 1, now it the span of this set, this means the span of this set, this will that form a subspace. So what will be the span of this space? It will be a plane in R3. Fine. The plane can be a subspace, but what could be the condition? What is the condition that a plane in R3 will be subspace of R3?
It has to pass through 0.
Right. That means the null vector should be inside that set. Okay. So since in this case the null vector will be within the span of these vectors, then the plane it will generate will, of course, will pass through 0, and in that case the span of these vectors will form a subspace in R3. Is this point clear? Excuse me. Please let me know if you have any doubts from this statement. Similarly, the example 2, what we discussed, that example 2, the span of, if I say that this is set S, then the span of S this we have seen that is the xy plane. Sorry. And of course, this xy plane contains the origin 0, and it will form a subspace. So in this case also, you can say that this set of vectors, these two vectors of the set S, generates that subspace. Okay. Again, if I said that S is this, then we have seen that span of S is the x-axis. So though there are 4 vectors, but it can, I mean, it generates the x-axis. Of course, we know that to generate the x-axis, the minimum vector we need, that is 1 vector. E1 will be sufficient, or any multiplication of E1 will be sufficient. But here in this case, there are 4 vectors. Of course, they are linearly dependent. But this set of four vectors, yes, they generate the subspace, which is the x-axis. Is it clear? So if you, the point is, if you are given a set of vectors, those set of vectors, of course, in the they may or may not form the subspace, or span of those vectors. Uh, then the question is, the span of those vectors will create the subspace or not. That is also may or may not, that we have seen in the examples here. But if the span of those vectors forms a subspace, then we will say that that set generates that subspace. Fine. Any question, doubts about this statement or about
Sir,
this
can
point?
you repeat the last sentence you said? I had a network issue.
Oh, what I said, that it's not necessarily that if you have a set of vectors, the span of that set of vectors will always create the subspace.
Okay, sir.
Okay. We also had an examples here. Okay, so no, no. What I mean that, sorry, the span of a set of vectors, whatever the subspace it creates, we say that that set of vectors will generate that subspace.
Okay, sir. Got it.
Okay. So, for example, the second example, the set S, which contains two vectors, generate the subspace, which is xy plane. Third example, those four vectors generate the subspace, which is the x-axis.
Yes, sir.
Now what? So this is the point. Okay. Now, today we discuss about some properties of the subspaces. So those properties are given in terms of theorem. And again, here I will not prove those theorems. So in the tutorial class, you, I mean, if you have a problem to with the proof, you can ask your tutors. But these proofs are also given uh, in the book of MAPA or any other books. So the statement I usually, for these theorems, I have taken from MAPA. The intersection of two subspaces of V, again, when I say V, it means V could be either R or R square or R cube. R3. Okay, V. So if we take the intersection, let's say that you have two subspaces. U is a subspace of V. W is a subspace of V. Then what's about, the question is, what's about if you take the intersection? Will that be subspace of V or not? So will it be subspace of V? What do you think? So how to check it out that that will be subspace of V or not? Any idea?
To see if it contains the origin.
Okay, first point, does it contains the origin? So U contains origin,
Yes,
W
sir.
contains origin.
So
So
it's there
U
in.
intersection W will also contain origin. First point, okay, fine. Now, if you take any vector, uh, let's say V1 belongs to U intersection W, and any other vector, let's say V2. Sorry, let's take V1 and V2 belongs to U intersection W. Then the question is, what's about any linear combination? Will that also belongs to U intersection W?
Yes, sir.
And what is the reason?
U and W is closer under addition
Sorry,
because
once
U
again.
and W is a subspace. So we can add the V1 plus V2, a linear combination.
Okay, so we can add the linear combination. Yes. So can you please elaborate it? You are
Yes,
probably in the right tag, but can you please
yes, sir.
elaborate your arguments?
V1 and V2 are, belongs to U. U intersection W is a, U intersection W is a subset of U. So U V1 and V2 is also belongs to U. So as U
Right,
is subspace, so we can do
right. So since since B1 and B2, they belongs to the U intersection W, that means the U V1 and V2. So they will, from here we can say that V1 comma V2 will belongs to U, as well as uh, V1 comma V2 will belongs to W. And since U and W are the subspaces, that means any linear combination also belongs to U, and also alpha 1, the any linear combinations of V1 V2 will also belongs to W, since U and W are the subspaces. Sorry. And this implies that this linear combination belongs to this. And this way we can prove that. Okay, so you go through the proof little bit in details, but this is the main idea of the proof. It is also a subspace of B. Okay, few comments on this. let's say you have W1 and W2 be two subspaces. I write down in short, let's say subspaces of V. Then of course what we have seen that W1 intersection W2 is also subspace. Not only that, that will be the largest subspace of V which is contained in W1 as well as in W2. I write down, then you read this and tell me that if you understand, if you have any problem to understand the statement. Then this is the largest subspace contained in W1 and W2 both. So V can have many subspaces, and okay, let's take an example. Let's B is R3. Okay, what's about this set? This is a null vector. Okay, so is it a subspace of V?
Yes, sir.
Yes. This null vector also belongs to, okay, let's say W1 is XY plane. W2 is XZ plane. So 0 belongs to W, and also this null vector belongs to W, and then, sorry, this not belongs to, this contained.
So the
Write
second
down,
zero
this is the subset. The subset of W1 is a subset of W2. Fine. But this is not the largest subspace of V which has this property. But in this case, the largest subspace of V which contained in both W1 and W2, there is the x-axis. And what is the x-axis in this case? That if you take W1 intersection W2,
Intersection.
right, this will give us the x-axis. So this is also subspace of V, and of course W1 intersection W2 is subset of W1 as well as W1 intersection W2 is W2. Write down this. Okay, now is the statement clear? Please ask me if you have any doubt. Please stop me and ask me the question. Also, we have another comment that If we have two subspaces W1, W2, the intersection will be also a subspace. It's also for finitely many intersection. This is also true for finitely many intersection. Since we purposely avoided the infinite stuff, so but if you are interested, you may think at home that what will happen that if you have countably infinite number of subspaces and you take their intersection, that will be a subspace or not. But if you take a finite number of subspaces and take their intersection, of course that will be is a subspace of V when Wi, where I equals to 1 to k are subspaces of V. I mean, you can iteratively show that it's so easy. Now the next property. So what we can see that if we take the intersection of two subspaces, that will be a subspace, also subspace of the same space. So what's about, let's say, W1 is subspace of, okay, W1 and W2 are subspace of V. Then what's about W1 union W2? Will that be always a subspace of V?
Not necessarily, sir.
Any example?
So if we consider V to be R2 and W1 as the x-axis and W2 as the y-axis.
Right. So not necessarily. What you said that W1 is the x-axis and W2 is the y-axis. Then W1 union W2, let's say that your V is R2. So W1 union W2 only gives you the vector either along the direction of x-axis or the direction of the y-axis, not other vectors which has some angle with the some non-zero and non-90 or perpendicular angle with x and y-axis. Okay, so that's why the union will not be a subspace. Of course, if it happens, let's say W1 is a subset of W2, that means W1 already inside the W2. In that case, W1 union W2 will give you the W2, right? In that case, that can be. So that is the case, only case when W1 and W2 will be the subspace.
Yes, sir.
And this is actually the only case. So that's why you can say that, let's say if W1 and W2 be subspaces of V, then W1 union W2 is a subspace of V if and only if either W1 is a subset of W2 or W2 is a subset of W1. Actually, this is the only case when they can be in the subspace. But what we can see that if this is not the case, that one contained in another one, this is not the case. What you gave us the example. Let's say this is the in R2, and is x-axis, this is our W1, this is y-axis, this is our W2. So we'll miss any vectors which are here, right? Only we can represent the vectors which are on the x-axis or on the y-axis. Okay. But what we have when we have W1 union W2, when we have W1, we have any vector. Let's say we have the unit vector along the x-axis. We have any multiplication of unit vector along the x-axis. The negative multiplications are also included. And when we have W2, we have any vector along the y-axis, even the minus y-axis, right? Now, is it possible that if I ask you to construct, let's say, this vector by adding one vector from x and another vector from y? That means I want a vector, let's say v1 belongs to x and v2 belongs to okay, let's say not x, this is w1 and v2 belongs to w2. And is it possible to construct any vector in R2 by joining v1 plus v2? Or in other words, does there exist a vector v1 in w1, v2 in w2, such that v1 plus v2 will be my desired vector? Let's say this is xy. Is it possible?
Yes, sir.
Yes,
Yes,
sir.
right. Because
But it's not in
not
it's not in the union.
it's not in the union, of course. It's not in the union because union gives you only the vectors along the x-axis, plus direction or minus direction, and all the vectors along the y-axis. But we can have these two vectors v1 and v2, v1 taken from w1 and v2 taken from w2, such that if we add these two vectors, then this vector can give my desired vector on the R2 plane. That means if we are able to generate a let's say set where the set will be consist of the vectors with this form v1 plus v2, where v1 is taken from w1, v2 is taken from w2, and all possible v1 and v2. So that will, of course, then generate the R2. So this kind of set or generation of set has a name. This set is the linear sum of two subspaces. And what you can see that when you take the union, So it cannot form the subspace because there are some missing vectors which we could not include within that union. And when you take this linear sum, it will include those vectors. So first I define that linear sum formally. The definition is, let's say, let U and W be two subspaces of V then the subset U plus W equals to let's say V1 okay, let's write down in terms of the way with the same notation. I use, let's say, W1 and W2 be two subspaces of V, and the subset, sorry, W1 plus W2. Here, plus operation, I mean, this operation is defined in this way. So this will give us a set where we have V1 plus V2 such that V1 is taken from W1 and V2 is taken from W2. So this set, or this subset, is said to be linear sum of the subspaces W1 and W2. Okay, is the definition clear? Let me know if you
Yes,
have
sir.
any doubt on the definition. Excuse me. Sorry. Now we have few notes. What's about the null vector? Will that belong to linear sum?
Yes, sir.
Why?
The null vector belongs to the subspace of W1 and also W2. So,
Right.
yeah,
Null vector plus null vector will give us the null vector, and then that's why it's will all belong also belong to W1 plus W2. Another thing we can see that, let's say V1 belongs to W1, and we know that null vector this belongs to W2. This implies that V1 plus null vector, sorry, this is equals to V1. This belongs to W1 plus W2. And this implies W1 is a subset of W1 plus W2. And which is easy to see with our example that W1, W2 will be the whole, in this case, whole R2. So that's why the W1 will be a subset of W1 plus W2, as well as W2 will be the subset of W2 will be subset of W1 plus W2. What's about W1 union W2?
That will also be a subset.
That will also be a subset. But on the other hand, we have seen that this forms a subset, a subspace. But this does not always form a subspace. We know that when does it form a subspace. But let's say in general case that W1 intersection W2 is not phi. In that case, W1 union W2 will not form the subspace, and also W1 union W2 will be a subset of W1 plus W2. Then what is the problem? Which are the missing part in W1 union W2? So there must be some missing part. Missing part means some missing vectors are there whose inclusion will make W1 union W2 a subspace, right? There must be some missing part or missing vectors. So in that case, when it will not be a subspace, in that case, W1 union W2 will be proper subset of W1 plus W2, right? Because there must be some vectors which are not in W1 union W2, but in W1 and plus W2, which makes the W1 plus W2 as a subspace. Just think at home that which will be those vectors. It takes just very typical examples from there also. You can have the idea that what is happening. Okay. Oh, we did not say. Okay, so we did not write down this property that W1 plus W2 will be subspace. So let's write down that let W1 and W2 be two subspaces of V, then the linear sum W1 plus W2 is a subspace of B. Sorry, we forget to discuss this part. We assume that we have already discussed that this will be a subspace. Anyway, so why this will be a subspace W1 plus W2? That we have seen for this typical example that W1 plus W2 will be a subspace. But because what we can see that, I mean, if if the vectors in W1 are linearly independent with the vectors in W2, which is the case we discussed here with this example. In that example, then the direct sum will fill up the rest of the space, right? So that means it will generate the whole space R2 in this case. And of course, if W1 contained in W2 or that the linearly some vectors are linearly dependent, then also, I mean, it can happen. So that means you have to consider few cases, the relation between W1 and W2, and then you have to proceed for the proof. But of course, we have seen that the null vector will also belong to W1 plus W2, and what you have to show that if you take two vectors which is in W1, if you take two vectors which is in W1 plus W2 in the linear sum, their linear combination will be also in the linear sum. This is not easy. This is not hard to prove it. You just must try. Otherwise, your tutor will show you the proof. And the proofs are also given in MAPA and other books, and they're very simple. Now, W1 and plus W2, this will form a subspace. This will form a subspace. Again, not only that, this will form the smallest subspace of V, which contains both. That subspace will contains both W1 as well as W2. First I write down, then I explain. The subspace W1 plus W2 is the smallest subspace of V containing W1 and W2. Okay. Let's say this is R3. This is x-axis and this y-axis. And the typical example we take, which will be easier for you to understand. Let's say x-axis is the W1 and y-axis is the W2. Or yeah. Okay. So in this case, what will be the W1 plus W2? If
XY
x-axis is
plane.
right, so it will be xy plane. And if you take any subspace in R3, R3 is also subspace of R3, which also contain W1 and W2. But we want to reduce its the number of vectors from that subspace. Okay? So if you reduce, then let's say xz plane, that is also subspace in R3, but that contains W1, but that does not contain W2. But on the other hand, xy plane, that is a subspace of R3, which contain both W1 as well as W2. So though R3 itself is subspace of R3, which contains both W1 and W2, also xy plane, that is also contain W and W2. So the xy plane is the smallest subset of R3, which contains both W1 plus W2. Other example, let's say that your W1 is the x-axis. And W2 is only the null vector. Okay. So then what's the subspace of R3 contains W1 and W2 both? The first one is R3 itself, contains W1 and W2 both. Second one is any plane passing through x-axis. Any plane. It could be xy plane, it could be xz plane, or it could be any other plane which passes through x-axis. Will contain both W1 and W2. And also the x-axis itself is the subspace of R3, which contains both W1 and W2. You cannot reduce more R3 and forms a subspace which contain both W1 and W2. So this is the smallest subspace, which is the x-axis. So smallest subspace of R3 in this case contains W1 and W2 is the x-axis. And this x-axis is actually, on the other hand, W1 plus W2, right? So that's why the W1 plus W2, it will not only form a subspace, but that will be the smallest subspace of V containing both W1 and W2. Is the point clear?
Yes, sir.
So any doubts, comments on today's class on any properties or any statement? Okay, so if not, then we stop here and we